Right, this video is about section 1.2, which concerns data, sampling, and variation, variation in data. We're going to see at the end. Uh, First, though, data, we're going to start to sort it into different types based on the way that we measure or express data. And the first one is called qualitative data. Another word for that is categorical, which I think is a good term to keep in mind because we're going to put data into categories. But this is an okay term too, but the qualitative means that we're putting data into categories based on different qualities that they have. So I have a way of describing this, which is that data that is qualitative describes attributes of a population. So it's got to be something that everyone in the population fits into some category or another. We may be measuring only data from a sample if we're doing sampling, but in any case, the whole population should be divisible into these categories. The other type is quantitative data, and that's data where the results of our measurements or however we get our data are going to be numbers, quantities. This is also called numerical information or numerical data. And that's a great word for it too, because it's got number or numeral in there. Data that can be represented with numbers. This is the result of counting or measuring attributes of a population. So these are both pretty solid, relatable definitions that show the difference here. This describes qualitative data or categories describe attributes. Quantitative or numerical data come from counting or measuring. I mean, it could be length, it could be duration, it could be mass, whatever it is. If you're measuring something or counting something, you're collecting quantity or numerical data. I'm going to go a little bit further into quantitative, which is based on these two things, really. The counting and the measuring. Those really are different things. And those give us ways to describe data even more precisely. First, discrete quantitative data. So we're going to see these words quite a bit. I want to use the abbreviation quant for quantitative, but discrete is what I'm going to describe here. But discrete only applies to quantitative data. Discrete doesn't really apply to qualitative data, but it is one type of quantitative data. Only certain values result from counting. Now, we are going to see situations where the numbers are not necessarily whole numbers. One example of discrete quantitative data could be shoe sizes. Right? So shoe sizes are whole numbers and half size numbers. So there's, for example, there's size 8, and there's size 8.5, and size 9, and size 9.5. But there's no size 9 3/4 or size 5.632. They're discrete, even though they're not always whole numbers. But the other thing, let me put a comma here. So only certain values characterize discrete data. Only certain values are allowed. The results from counting, actually a semicolon would go there. The result of counting gives us discrete. So either one of these situations. But shoe sizes is kind of a familiar one. The other one, the other type of quantitative data is continuous quantitative data. And continuous means, in this case, that between any two values of data, there's a bunch of other values between any two values. And this has the characteristics of the real number line, or the number line that you're familiar with, not just the whole numbers, but all the real numbers in between. These continuous quantitative data results from measuring. And that's the key idea, is things that you measure, like length or duration, how long something takes, or weight that you can measure with a scale. Those are the type of things that make up continuous quantitative data. So let me put up a little example here. Height of people. Actually, we would say heights of people, because people have different heights. And that's one of the ideas that we're going to get into a little bit later, about the differences that we see in data sets. That's the idea of variation. All right, I have an example that's actually, it's a bunch of little examples that are going to give us some more ideas of what discrete and continuous, as well as qualitative data. So here's my example. Yeah, we're going to start with qualitative, or the categorical data. So one example of qualitative data is hair color. We could have a lot of different hair colors in a population. There can be black and brown and blonde and white and gray and bald, purple. There are people with purple hair and green hair. So hair color is qualitative data. It's not something that we're going to measure with a number for an individual. Blood type. Blood type is another qualitative. There are 8 blood types, I think. O, A, B, and AB. And then there's a positive and a negative for each one, but those are qualities or categories. Ethnic group, whether it's based on genetic material or based on cultural ancestry or origin. Ethnic groups would be examples of types, not something that we can assign a meaningful number to. And type of car. Now you could assign a numerical category to type of car if you're doing it by the year, but that's not what people mean by type. They either mean, is it a passenger vehicle or a cargo vehicle or a van or something, or maybe they mean what is the manufacturer of your car. So that's qualitative. The next two, I'm going to do quantitative, discrete first. And this is DISCRETE. It means in individual separate portions or measurements or counting. REET, discrete, is a completely different word, and it means to be appropriately private with information, basically. This is a different word. It means, I like to think of it as bite-sized rather than Like, for example, nerds candy are discrete. Nerd rope is continuous, though. It has a length. You can have a 1 foot nerd rope. You can have 2 foot nerd rope. You can have 1 3/4 nerd rope. It's a continuous quantity. My examples for this one are number of phone calls per week, that you get, for example. It could be number of calls per week that a person at a phone call center gets, and that would be a much higher number, I hope. But whatever it is, the number is what gives it away as a discrete quantitative variable. Number of books in your bag. In the past, classes would meet all in the same room and everybody would gather to the same place, and people would bring their bags of books and things before all this. Okay, so yeah, the number of books, and that's the thing that gives it away, number of. The other one, quantitative continuous data would measure, for example, some of the following things. The weight of the books in your bag. So altogether, I mean, each book has an individual weight, sure, but if we're talking about the number of books in your bag, that's how many there are. The weight of the books in your bag is the weight of all of them, basically the weight of your bag, probably. And then I have another example of a quantitative continuous measurement in the distance from home to school. So everyone lives a certain distance away from school, and for each one of those distances, we would have a number that would be measured. You could measure using counting, like if you wanted to measure the number of steps. That's a discrete way to measure it, but we usually think of distance as something continuous, a number of miles or a number of feet or number of meters. So there's some examples for side-by-side comparison of qualitative, quantitative discrete, and quantitative continuous data. And I have a little tree diagram that helps me to organize this. So data is divided into two main categories. I'm just going to say qual for qualitative and quant for quantitative. Things that are described with qualities and things that are described with quantities. And quantitative data further breaks down into discrete and continuous. And with these abbreviations even, this makes it really easy to write. These are good abbreviations because a lot of the answers to the problems are going to be using those words. And if you write the abbreviations instead of writing the whole word each time, it'll save a lot of writing time. The only thing is both of these words start with a Q. So you can't really use Q, just the letter. You could say D and C for discrete and continuous. Oh yeah, I have an example of exactly that. This is going to be more writing than I really want to do, but it's good to have these things down just for reference when you're doing your own work. We're going to decide which type of data. And the choices are qualitative, quantitative, quantitative discrete and quantitative continuous. So each of these types of data kind of fits into one of these categories. Some of them are arguably in more than one. There's more than one way to interpret. And in normal class, we could have a discussion about this. I'm just going to have to give my opinion instead. But for part A, the problem is, or the question is, the number of pairs of shoes you own. And each person has a number like this. It could be 0 if you just don't own shoes, but it can't be negative. You can't have a negative number of shoes. Also, we're talking about pairs of shoes. So if you have one shoe, that's not a pair of shoes. Number of pairs of shoes. This is a number, so it's quantitative. And it's not a measurement, but a counting number. So this is an example of quantitative discrete data. For part B, type of car. You drive. So I would say, just with no other context than this, they're talking about, do I drive a Cadillac? Do I drive a Honda? Do I drive a Schwinn? I mean, not a Schwinn. If you don't drive a car at all, that's a category. And each of those types of cars would be an example of a qualitative piece of data. So I'm just going to say qual. Your last vacation destination. And it's not talking about how far you went or how long you stayed. It's the destination, the place that you went, and that's a category. There's no way to meaningfully enumerate or measure and rank the destinations. This is another qualitative. I've got up through number n, so I think that means there's 14 parts in this problem. I'm gonna have to erase this to keep going, but we'll get to some more interesting ones pretty quickly. So part D is the distance to your grocery store. So the grocery store that you usually go to, how far is that from your home? And that's kind of a meaningful statistic for people. That's where you get your food. Everybody, well, not everybody travels to get their food. Some people grow their own food, but most people go to the grocery store. How far is that? Distance. It's measuring a length of space. This is quantitative. And since it's a distance, not a number of things, it's quantitative continuous. The number of classes you take each year. So this is assuming that you're a student, and really you could include everybody here, because if they're not a student, they take 0 classes. But if you're measuring only students, it means you take at least 1. And like if you take 5 in the fall and 5 in the spring, that's 10 classes per year, for example. It's a number of. This is quantitative, so because it's a number. And discrete, because it's the kind of thing that we can count, 1, 2, 3, 4, etc., not something that we measure. Your tuition. So if you do go to school, you probably pay tuition. And people pay different tuition based on where they go to school, how financial aid treats them. What else? Well, some people pay tuition with loans, and I'm not sure if that counts as you're paying it now, but that's still your tuition, whatever your bill is for your classes. That's quantitative. And, all right, here's the problem. Money. Is money continuous? Now, I can only go down to a cent. A half a cent has no meaning to me, either giving or taking. A cent is the smallest unit of money that I can use. There are financial organizations on Wall Street or whatever that do banking where fractions of a cent are involved. And it's meaningful. They make money or something like that. So, but also sometimes it's just convenient to think of money as continuous. Like there are people that make all different ranges of money. Well, strictly speaking, each year, each individual makes an exact number of cents or pennies. And that's as far as you can divide money in the ordinary sense. But this one, I would say, is quantitative continuous or quantitative discrete. I think there's an argument for either one or both, really. You kind of have to pick, though. You can measure it as a real number, or you can measure it as an absolute number of cents. G says the type of calculator you use. Now, your calculator might have a number as part of its name, TI-36, TI-83, whatever. But that number is not a meaningful, it's a name. It's not like a quantity that if I have two 36s, sorry, if I have three TI-36s, is that better than a TI-83? That's not how that works. These are types, and this is an example of qualitative data, the type or the category of calculator. Of course, there's more than Texas Instruments. There's Hewlett-Packard and whatever other Casio brands that make calculators. Those would be categories. H. Movie ratings. Now, I'm going to say movie ratings can be qualitative because they can be like the thumbs up, thumbs down, good, bad, or maybe 2 thumbs up, 2 thumbs down, or 1 thumb up, 1 thumb down. It's still, those are kind of categories. Qualitative, quantitative, discrete, because movies can be rated on a 1-star through 5-star scale. Those are discrete numerical ratings, 1, 2, 3, 4, or 5. Maybe 4.5. That's still discrete though, because we're not going down to 4.3 in any real number, just the whatever our categories are. But they're numerical, they're quantitative, they're ranked. Or continuous, I think it's Rotten Tomatoes does their movie ratings by a percentage scale. And really that could be, maybe you could say that that's on a scale of 1 to 100. But really this percentage kind of makes it look like it could be any real number between 0 and 100. Movie ratings. Political party preference. And there's no real way to assign meaningful numbers to the different political parties. So this is an example of qualitative. There are different categories, the red party and the blue party and the green party and the other party. Weights of wrestlers. weights of wrestlers. So this is especially in the Olympic style wrestling, it's really important that people wrestle people that are in their same weight class, whatever that is, people that are close to them in weights, for fairness and sportsmanship and probably safety. But weights are that kind of measurement that you make with a scale that can be really any number. So we can have decimals. You could consider weights as being fractions or something, but these are definitely numbers, so they're quantitative and they're continuous, because between any two weights, there's still other weights. No matter how close those weights are, there's still weights between them. K says amount of winnings in poker in dollars. And I'm going to go ahead and say for this one, because it's amount, it's quantitative. But for this one, they're talking about the number of dollars. How many dollars? Don't worry about the cents at all. It doesn't really matter. It's less than $1 anyway. But the number of dollars is what it seems like here. Amount of money could be continuous, but I think quantitative discrete is a better description of this particular example. All right. JKL, part L is a number of correct quiz answers. Or in other words, the number of answers that you get correct on a quiz. That's number, definitely quantitative, and discrete, because and the way that it's presented here is correct. And if you're just counting the correct, I'm not talking about partial credit for the wrong ones or anything, just the number of correct answers. That's either you got it correct or not quite. And if you got it correct, you count it. And that means this is kind of discrete because we're counting the number of correct answers. Part M, people's attitudes toward government. I don't think there's a simple way to measure this with a number. People have attitudes of like in favor or not so in favor, but they also have attitudes that are extreme or mild. So there's a lot of different things that could be attitudes toward government. I'm going to say that this one is qualitative. And then finally, IQ scores. There's a few things here. With IQ scores, depending on how you look at them, they can be quantitative, discrete, or quantitative, continuous. Now, they're definitely quantitative because the IQ score is a number. The average IQ, I think kind of by definition, is 100. Below that is below average IQ. It doesn't really mean below average intelligence, and vice versa. Above 100 is above average IQ. It doesn't necessarily mean above average intelligence. Something like that, though. It's a measure of intelligence. When you take an IQ test, you get a whole number. So in that sense, this is a quantitative discrete data type. But if you average a bunch of IQs, or you're measuring an IQ scale and looking for patterns in it, you're really treating the IQ scale as a continuous quantity. So I think either one of these is an okay answer for this, as long as you can give some kind of justification. I want to next go over a couple kinds of display of information, we're really not going to use pie charts. Pie charts are a presentation of data that would be like a final product of research just to display results. I want to mention what they are, though. Pie chart is where categories are wedges. Wedges in a circle. So we would have a circle with maybe a big wedge and a big wedge, and kind of a big wedge and some smaller wedges, and then the smaller ones, whatever it is. Each wedge or section of the pie represents a different part of the data set. Looks like I've got, I don't know, maybe it's 30% here, and 20% here, and 15% here, and 10% here, and then less and less as I get to the smaller and smaller wedges. Like I said, we're not really going to use pie charts very much, but bar graphs we're not specifically going to use bar graphs. We're going to use a very specific type of bar graph. But in general, bar graph works like this. Length of each bar is proportional to the number of individuals. In that category of what the thing is. So if I did a bar graph, this isn't really supposed to be a number line, it's just a place for me to organize my data. If I measure people's hair color, I'm going to measure how many people have brown hair, how many people have black hair, how many people have blonde hair, how many people have red hair, how many people are smooth. Maybe other, or I could get more colors too, but I think the brown hair would be the largest rectangle. The black hair would be the second. Blonde would be kind of small. Red would be pretty small. Smooth might be a little more than red. But the bars, the height of the bars, or the length of the bars, is proportional to the number of individuals. So there's more brown people, longer brown bar. Fewer red people, shorter red bar. We're going to be more precise about how we build these sort of things later. But I just want you to recognize bar charts. The other thing that I want to point out about this is there are gaps between these bars. And that means something. Basically what that means is that these are categories. I'm not saying it's impossible to have hair that's between brown and black, but for the purposes of this tallying or measurement, we need to put everybody in one category or the other. And so these categories are distinct. We're going to see later on what it means when there's no gaps between the bars of the graph. Okay, next, I've got a little bit of detail about the process of sampling. So think of sampling as how you get your sample, which you then measure, and then those measurements become your data. First, a census gathers data from all members of the population. Everyone. And you might be familiar with the US Census. I don't think they gather data from everyone, but they really, really try, and they spend a lot of money doing it. It's extremely expensive to track down and make sure that you're not double counting the same people, but also get everybody. And it's a good thing to do probably for government, but it's very difficult and expensive. And in general, we don't do census. Unless your population is very, very small, it's too expensive to do a census. A sample gathers data from a subset of a population. And the population, that context is very important here. But we're only going to get our data from the sample that's drawn from that population. A representative sample has the same characteristics as the population. And it's a sample, but representative is the key here. Does the sample represent the population? Or does it represent it accurately? That's the kind of sample that we want. It might be easier to get a different sample, just the closest people to you, but really a representative sample is more likely what we're going to get from a random sample. Is chosen randomly. I don't know how else to say that really. It's somebody that, or it's a sample that for each individual we're randomly selecting from the population, trying to avoid any pattern of how we select our sample. Now it's harder than it sounds to be really, really random most of the time. A random sample usually gives a representative sample. And in that case, randomness, which we usually think of as an opponent, like something we have to combat, randomness in this case works in our favor. If we're random, we usually get a representative sample. It would be extremely unlikely to pick a sample at random and have one that's really lopsided. So I've got a couple other terms to go along with this. The first is simple random sample. Any group of n individuals is as likely as any other. Group of n individuals. Kind of a mouthful there, but a random sample, our size is going to be denoted by the letter n, n for number, but n. And that particular, well, random sample is just as likely as any other random sample. That's what simple random sample means. A true random sample, actually, I don't think we really need to get too far into true random sample because we don't do it that way. But a true random sample, an individual that we select for our sample gets put back and can be picked again. So you can have a random sample that contains the same individual twice. And that's a little bit of a mind bender, and it's a little more complicated than we need to do. We're going to do the simple random sample. N individuals, N different individuals, randomly chosen, make up the sample. Simple random sampling is done without replacement. We'll get into that term more later. And then finally, This is a word I mentioned earlier, variation. Variation is the differences in the data from a sample. So if we took a whole sample and everybody in the sample had the same measurement, they would have very little information. It's the differences in the individuals that make variation, and it's the patterns in those differences that we're looking at. So math in general is a search for patterns. Statistics is a search for pattern in data. And variation is that thing that makes the data different, that we can look for the patterns. So I'm going to just say variation in data. It's the differences between data values. And I don't mean the difference as in subtract them, although if you wanted to find the difference between two data values, you subtract one from the other. But this is just all the variety, variation, and the word that this actually connects to is, that we use all the time, is variable. The variable that we're measuring shows the variation that we're studying.